It makes it so much easier. Yeah. So yeah, we are always looking for anybody with any botanical skills. Botanists are really hard to find. So anybody has got that is great.
We have a general, unfortunately it's not wetland specific, but most of these ecology folks will be required, and some of the environmental science that have a wetland focus will be required to take our plant systematics. So it covers mostly the more terrestrial groups, but it's a ton of plant taxonomy in general. So it's sort of like there's a whole bunch of stuff that's out of the way because of that. And then I'm trying, best we can this time of year, next week to start picking up some of the, really obvious plants. So we just talk about a few every time we go out, and then we'll have one big veg day. So
nice. Yeah, no, I mean, there's, a ton of crosswalk there. I think the only thing missing probably is the carex if you just do an upland.
Yeah.
Of course, but still, just being familiar with using a dichotomous key is huge. That's great.
They end up with the plants of Montana kind of glued into their hands, and then we'll have that the green wetland plant. But for the state in ours. So.
Nice.
Well, I think we probably have kind of critical mass. So if you're okay, we'll get going. How's that sound?
Sure, that sounds great.
Awesome. So thanks everyone for coming. This is the third in our Life In and Out speaker series that the biology department is hosting this year. And as we often do, we try to pair these talks with a class. So there's a wetland class going on right now. And then what are a couple of the environmental science classes that are, we got sustainability, and then is it
weather and climate?
So weather and climate. So all of these kind of coalesce around this idea, concept, and discipline of wetlands. So I asked Jennifer Jones to speak with us today. I met her at a wetland plant training this summer. She's an ecologist and project manager with the Ecological Mapping, Monitoring, and Assessment, or EMA group, after working for the Montana Natural Heritage Program for a number of years. She received her bachelor's from North Carolina State University and her master's degree in ecology from Colorado State University. And at EMA, she oversees the wetland and riparian-related projects and full field work in conjunction with a lot of federal and state partners, which, as we've talked about in wetlands, is often the case. And her background is in wetland and plant ecology, pretty much all over the Rockies. And she's based out of Bozeman. And so she's going to tell us a little bit about her program and some cool modeling they've been doing related to wetland function predictions. So, take it away.
Great, thanks. Thanks so much, Michelle.
Thank you.
So, let's see. I appreciate you having me. Thanks for introducing me, so I don't have to do that. So I'll start by providing you a little more information about our group, the EMA group at UM-Missoula. And then I'm actually going to give you a pruned version of this automated LLWW model that we've been working on for the past couple of years with a few partners in the state. It sounds like you guys have been working on some classifications, so a lot of this will make sense to you. This presentation was actually first given at a National Association of State Wetland Managers presentation series, and the model was still in development at the time. But now it's been actually applied to multiple wetland mapping products in the Western U.S. We do a lot of WAP mapping right now for the BLM. And the Forest Service, if we can get funding from them, and anybody else who wants mapping, we'll do that for them for their wetlands. It was presented originally by Sarah Owen, who's now actually moved on. She works for the National Wetlands Inventory now as a senior wetland coordinator. The model developer, Eric Dressing, still works for us full time. So if anybody is a GIS modeler, and they want to hear some more nitty gritty about the model, he is definitely available to chat about that in more detail. I am not a modeler. I'm not a GIS modeler anyway. But I can answer, try to answer as many questions as I can about that piece. So the EMMA group, a little background about us. We're the Ecological Mapping, Monitoring, and Analysis group at UM. As your professor mentioned, our major projects are with the BLM. We do assessment, inventory, and monitoring in terrestrial systems, aquatic systems, and riparian and wetland systems. And we also do a lot of wetland mapping. And we do, for the EPA, we do a lot of wetland program development grants. And so we do a lot of soft-funded projects. We currently have about 30 year-round employees. A lot of those folks just started doing wetland mapping for the winter, and they'll transition over into doing field work for us in the summer. We have about 60 folks in the summer, and I'll do another little plug. If any of you guys want to do field work in the summer, we are definitely open to having crews based out of Dillon. If you have housing there, we'd love to do that and have some crews working in Idaho. We have a bunch of projects in Idaho this summer. So we are always looking for folks with a background in any kind of ecological work. If you're in a program like this, if you've had any wetland background, that's really great. So in the off season, like I was just saying, we have about 30 folks, about 20 folks actually that are doing wetland mapping, and that involves photo interpretation of aerial imagery and creating wetland feature layers and assigning National Wetland Inventory or the coordinate classes to those feature layers. And so the work I'm going to present on right now comes out of that wetland mapping work. So we'll develop the wetland mapping, and then we like to, if we can, develop more advanced wetland mapping products for land managers to use. And so that's what this is about. So LLWW. I'll give you, this is just a little overview of the talk. I'll give you a little background about LLWW. What is that? What does it mean? And next we'll discuss how that's derived from the NWI, which is the National Wetlands Inventory data, and what additional data you need to assign those LLWW codes. And then I'll walk through the automated model in a little bit of detail, and then I'll provide some example of model outputs and how those can be used by managers. And so you guys sounds like you're talking about wetland classification systems. There are quite a few to choose from out there. So LLWW is basically just another system of wetland classification. And they're wetland classification systems that are based on a number of characteristics such as hydrology, geomorphic setting, vegetation structure, or even some of there's on specific plant communities or plant associations. And some of these classifications are geographically restricted, like the Montana one that you guys have been using, and they may be for a particular state, while others are based on ecological systems covering wide geographic ranges like North America. So the foundational classification system for the National Wetlands Inventory, as you guys have been learning, is the wetlands and deep water habitats of the United States, and it's commonly referred to as the Corden system, and he was just the main author on that paper. This system focuses on vegetation, structure, and water regime characteristics in a wetland. And by water regime, I mean the frequency and duration of inundation or saturation in a wetland. And so that captures one piece of the puzzle. And so that was created in the 70s, and those were the things that were of particular interest to the Fish and Wildlife Service when they created that system. And so that's what's applied to do wetland mapping. So it doesn't address any physical pieces of the wetland, except for that water piece. So it doesn't look at where it is on the landscape, how it's connected, or any of those kind of things. So it wasn't until the early 90s that Mark Brinson developed the hydrogeomorphic system. And it sounds like you guys have had a little familiarity with that. That's the HGM system. And this classification system works independently of the system used for mapping, unfortunately. And so it was based on geomorphic setting, water source, and then hydrodynamics. So it's more physical classification system. And then it was used to crosswalk to function. And then, so in I guess it was the mid-90s, Ralph Tyner and the Fish and Wildlife Service realized that there was a need to crosswalk these two things, the National Wetlands Inventory with the HGM. And so Ralph Tyner created the LLWW coding system, yet another classification system to bring those two systems together. And so LLWW actually stands for landscape position, landform, water body type, and water flow path. So the LLWW specifically categorizes wetlands based on geographic characteristics as opposed to other physical characteristics like vegetation or water regime like the WI. And so each of those 6 letters corresponds to a different hydrogeomorphic characteristic. So the landscape position piece is kind of the 30,000 foot view of where a wetland sits on the landscape. So so if it's a river, so the Lodic, so you'll see here, I don't know if you guys, oh yeah, can you see my cursor?
Yep.
Okay, great. So Lodic is the LO. Basically, if it's associated with a river, it's a Lodic. The lentic features, let's see, those lentic features are associated with lakes. And this is, I think that might be a BLM term, the Lodic versus lentic. I like to think of Lodic as lots of water flowing through those rivers. Lentic, it's, you know, the water is sitting and not moving. I think of lent and a belly button. I know that's a little bit weird, but it's stuck in my head like 20 years ago and I can't get it out. So lentic is for lakes. And then terrene features are those features that are not lentic or lodic. So that means that they're just not associated with a river or a lake. They often are surrounded by uplands. So those are the terrene features, and that, you know, that word terrene kind of makes you think of uplands. And so we'll discuss the landform and water body separately. Let me go back here. So these are mutually exclusive. You can either have one or the other of these, right? And so let's see. So water bodies, fairly obvious. They're streams, lakes, ponds. And then the landform includes all the wetlands that are not water bodies, so wet vegetated wetlands that, or ones that have exposed rock or mud substrate. And then let's see. And then the water flow path, also fairly obvious: inflow, outflow, vertical flow wetlands where the water comes up and down like a depressional wetland. Through flow wetlands, all those lodic wetlands where the water's flowing through either subsurface or on the surface. And then these through flow bidirectional and bidirectional are more lakes that are going up and down, or they have wave action. So those are the different pieces of the puzzle. So why would we use LLWW? The nice thing about LLWW is it allows you to highlight the potential wetland function at a larger scale. So this is not something you would really use when you go to a wetland, but it's something that like managers can use at a bigger scale, like a management unit or a state or that kind of scale. That's what we're looking at. And so the nice thing about it takes the 4 hydrogeomorphic properties. So these are those HGM properties that you guys are going to learn about here soon, and then it combines them with the coordinate pieces, so the water regime and the vegetation structure of a site. And then it comes together to give you a 6-letter code like we saw in those other in the mapping there. And then that can be crosswalk to the potential wetland functions. And so you can look at, you know, that all these certain types of wetlands are going to have these certain functions, and then you can do that at landscape scale and add that to your mapping. So just a little bit more background about how this developed and where this came from and the funding came from. The University of Montana in 2017, we started working on this. It's been a really long time to work through to get to this point. So they started working on a model back then, and then 2018, the Colorado National Heritage Program actually updated the Tyner key to make it specific to these Western states that are in blue. And then recently, in recent years, we started working with St. Mary's University, who they have a spatial analysis program, and they do a lot of wetland mapping in the Western US, just like we do. And so now we're working together on a model, and basically we've used that model for the past couple of years, and we're just kind of amending it. It's going to be iterative as, you know, we get better data and better spatial data to make those layers better. Let's see. So the most important input we derive LLWW from is the wetland mapping itself. So all those folks that were just getting started actually this week, their wetland mapping, that's probably the most important base part. Another important input is a subset of LLWW modifiers that must be assigned manually. So those are things like excavation, or if the wetland was excavated, if there's beaver activity, those kind of things, those are modifiers. And some of those have to be done manually in the imagery. Like you see them in the imagery, we don't have layers of those pieces. And so some of those definitely influence. So here are some, there's IR is irrigation, DS is discharge to stream, and AG is ag influenced. So those are just some of the modifiers. They're just the 2 letters on the end of that coord and code. So there's 5 dozen. So this new LLWW key that was created by the Colorado Natural Heritage Program has about 5 dozen modifiers. So it's a lot to deal with. So these are the automated ones, the ones that are in red. And then let's see, the ones that are in green might be automated, but most of those have to be done by hand. And so that's still an important part. You know, this automation is not getting rid of the human component, that these have to be applied manually. These are very important. So some of these like oxbows, discharge to stream, those are really important to the model, and they actually inform the model as it moves through and makes assignments. So a couple of these modifiers, irrigation influenced, discharge to stream, spring fed, and oxbow. Just a little bit about these irrigation influenced wetlands or wetlands that have been created due to leaking irrigation canals, or they may have floodplain. They may be floodplain wetlands that are wetter now because of canals. And so you'll see this in imagery when you see a ditch or a canal. You'll see some kind of seeping down from the canals. And so those are irrigation influenced. By discharge to stream, what I mean are these wetlands that act as a source of water for a stream network, such as springs and headwater wetlands. Spring-fed wetlands are those that are supported by point source or regional groundwater that can be seen in imagery or were previously mapped, but a lot of those have to be manually added into the mapping. Oxbows can be large natural lakes that have been cut off from a river usually they're associated with larger rivers, and they may be relic channel scars, as shown, and you can see them in this aerial imagery. All these little channel scars are oxbows. And then let's see, the last one, let's see, I think I got through all of those. Yeah, those are the ones that are important to the model and a lot of times have to be manually added. So the next big piece of data that goes into the model is the National Hydrography data set. And these are flow lines, water bodies, and points. And they're a layer that's created and maintained by the USGS. The final inputs needed for the model are a series of layers that are derived from elevation data, so a digital elevation model. And those include lake basins, a 100-year floodplain, a slope layer, TPI or topographic position index, and a layer of headwaters. And the example shown here is the topographic position index. These data are derived from a 10-meter digital elevation models, which is a little course. In the future, we would love for everywhere on the landscape to have LiDAR, and this would really help these models, but we don't have that yet. But you know, as we get more information and more of those data, more less coarse data, we'll be able to inform the model a little better. And then once all these data layers are gathered together, they're brought into a ArcGIS model builder. And so I don't know how many of you have done any model building. They can be shown as a very simple model like this, but they're quite complicated actually. And so this is a simplified graphic of the model workflow. The primary input, like we just talked about, is the wetland mapping layer for the target area. So for most of these products, we've done them for like a BLM field office, so a portion of the state, and on just the BLM lands that we've been mapping. The second major input is that NHD, or the National Hydrography data set. And then working from left to right, and then those manual modifiers. And so then working from left to right, the model adds in the water body descriptors and their flow paths. Those are first assigned because they're just kind of easy to pull from the model. Then the elevation derivatives enter to assign the initial modifiers, many of which are pulled directly from the Gordon codes, like B, the little b for wetlands that are influenced by beaver activity. And then as the model progresses is actually iterative and informs itself, such that the LLWW codes that are assigned earlier in the model are aided in decision making later in the model. So that's a lot of the connectivity will impact like flow path and landform and those kind of things as the attributes are added through the model. So for this prairie pothole, I think everybody knows what a prairie pothole is. Maybe you guys have talked about it. Those are in the prairie lands. You know, eastern Montana has a lot of prairie potholes, and those were glaciated. That area was glaciated, and they left these depressional wetlands. And those are considered terrene, basin, vertical flow. So they're terrene, they're usually surrounded by uplands. So they're not connected to rivers or streams or water bodies. They're basins, so they're depressional, and they have vertical flow. The water goes up and down in those systems. So that kind of helps you understand how you're getting to that code. So a little bit about the model. There's some things that work. There are some things that didn't work so well. You know, some of the things that work great, obviously, are the things that are pulled right from the Gordon code and the things that are automated. So water bodies worked really well. Landscape position worked really well. The things that are tied to the NHD data work really well. The Lodic floodplain and Lodic friend features were correctly assigned with high accuracy because many of these features, like I said, were directly pulled from the Gordon code. Some of the things that didn't work really well, I actually pulled this slide out because it was so complicated and got into some nitty gritty details about the model that it was a little bit hard to explain in this setting. Some of the things that didn't work well were really based on the digital elevation data. With that 10-meter digital elevation, that means 10 meters could be off on the elevation. And so those models and those derived layers are just a little bit coarse for those pieces. And so if there's a really subtle depression, a lot of times the model has a hard time catching that and calling that a basin or those kind of thing, or assigning the water flow correctly. So we're still working on that. We're going to be testing that in places where we have LiDAR, and that's that very, very fine imagery that you can actually look at. You can determine vegetation cover based on LiDAR because it's so fine. And so we're working through those pieces now, and it's going to be, like I said before, an iterative model that's just going to get better and better as we work on it and apply it in more systems. Okay, so how do we get to function, right? We talked about that. We got the classification. We're throwing all these codes together. So what is that going to do for a land manager? Basically, how we get to function is we, apply those codes. So let's take, for example, a spring. In this system, you can see this beautiful little spring where the water is just emerging out of a slope on the mid slope here. It's terrene. It's surrounded by uplands. It's sloping, and it's got what's called outflow for the flow, right? So water is coming off of or out of the slope. It's expressing mid slope at this site. It's not coming in from anywhere. It's just it's expressing right there to the surface, and then it's going out of the wetland. So that's why it's called outflow. So for this spring, this is a vegetated spring polygon that's been assigned that terrene slope outflow. And if you have a water body at the spring, that would be called a terrene pond outflow. So for this, we'll look at three examples, three different functions that can happen here: stream flow maintenance, surface water retention, and then other wildlife habitat. So as represented in these equations, so we've got these little equations. You can see the terrene slope. You can see terrene slope and outflow. and you can see that they're given a moderate or high. And so this is kind of what we've done, and we're still working through perfecting this, because sometimes you get the output and you look at a wetland and go, I don't think it probably does that. So this is all still a work in progress, and we give it to our partners, and they give us feedback once they use the data output. And so you can see for these different equations we've got. For these different functions, we're saying terrene wetlands in this system, a terrene wetland would have high surface retention, surface water retention for the ponds, right? And stream flow maintenance, it's high for outflow wetlands. And so we've assigned those, and that was work with a huge partner group. We had a bunch of wetland ecologists come together and talk about these different functions and say, okay, for terrene wetlands that are surrounded by uplands, what do we think are the functions that they do the best? And then we did an exhaustive literature search to inform those decisions too. And so those scores are combined, and then we get to a final score for each of those. So for the stream flow maintenance, we think that these terrene outflow wetlands have moderate function for stream flow maintenance. They have high function for surface water retention, and then they also have high function for other wildlife habitat. And we know that these systems are actually very, very important for wildlife springs. And so that's kind of how we're getting to the end score. And then we're in the process of updating these functional crosswalk matrices based on that new Western key. And we've kind of gotten to the point where we've done this, and we've provided it to some land managers, and we're in the process of having some back and forth with those folks to see if they think what we've assigned to those systems works. And so here's another example of what a land manager could do for a specific function. A synoptic map is kind of just an overall map, and that's what this is for a watershed in Montana, to look at potential function at this watershed scale. And so if wildlife managers say wanted to know, will minimum stream flows be met for fish in this watershed? Here she can display the functional scores, right? So these are functional scores for stream flow maintenance in a map like this. And in this example, wetlands with high potential for stream flow maintenance are shown in red. So these are the high elevation wetlands that are going to be putting into the stream and putting water out into the streams throughout the season. And then let's see, those that with moderate potential are shown in blue. And these are wetlands that are, like I said, are likely to retain water during snowmelt and runoff and release the water slowly over the growing season. So those are really important. So these wetlands include places like beaver habitats, beaver complexes, headwater wetlands, oxbows, ponds, fens, and those kind of wetlands are important for stream flow maintenance. So at a glance, an entire watershed can be reviewed for areas where stream flow maintenance are most likely to be maintained late in the season. And so this may allow these managers to target areas in need of restoration or identify wetlands that may be resilient to climate change. And so that's how we're hoping, a couple of the ways that we're hoping managers can use these kind of data. So here's one of the limitations that we've seen. As you can look at this larger stream system, and it looks very disconnected. So the Lodic systems are in blue, the lentic are in this kind of yellow color, and then there's some terrene systems in green. Those look very disconnected. There's not a whole lot of connectivity in those wetlands, and the reason is because non-wetland riparian areas are not included in this mapping. So our current model is based on NWI data. Not all areas have riparian wetland mapping. And so in this area, in this mapping here, you can see the riparian areas added in, and that there's a lot more connectivity there. So you would see there's probably more canopy cover, providing shade for fish habitat, leaf litter inputs contributing organic carbon export, those kind of things. Riparian habitat is also very important to floodplain storage and groundwater discharge that supports in-stream flows. So with the inclusion of the riparian mapping, you can see a more complete picture of potential functions of the floodplain corridor. So the original model did not include these riparian. We actually got funding since this first presentation was given by the EPA to add in and create a new model for the riparian mapping. So that's going to be happening actually starting this winter. We'll be adding those pieces into the puzzle. So quick summary, LLWW predicts potential wetland function. If you want to know what a wetland, how a wetland is functioning, you actually have to go in the field and look at condition, physical and biological condition of the site and see if that function is being met, if the functions of that wetland type are being met. So which is good for all of us who want to go out in the field, you know, we need to be able to actually look at what's out there. You know, you can only do so much through imagery and modeling. So the automated model works well for most of the LLWW codes. You know, like I said earlier, if we had LiDAR for the entire state, that would be lovely. You know, and we're trying to work in places where there is LiDAR and try the model in those locations. There is talk of getting LiDAR for the entire state of Montana, and so hopefully that'll come through in coming years, and we can update the model based on that. So with this new LLWW modeling, we're hoping that wetland managers can get a better idea of where certain wetland functions are taking place on the landscape, and they can use that information for restoration, landscape scale management. We definitely have BLM folks that are very interested in using this model on their field offices in Montana, and we've only done it mostly in other states now. So we're working, you know, to get there for the state of Montana. So just a quick thanks, EPA Region 8 are the folks that funded most of this work, and the BLM who are we doing mapping for, and they want this product. I've basically appended to their wetland mapping this code with the potential functions. And so those folks have funded this. St. Mary's has been a great partner. These are some of the folks, Joe and Jen and Jamal are the folks who kind of started this process years ago. And then Eric Dressing, like I said earlier, is the person who really built the meat of the model. So thanks to all those people. And then all these great functions, all these beautiful pictures of wetlands in the state of Montana to close. And then, so we can go with questions if anybody has questions about the model. And then I definitely wanted to get a quick plug in for our field work for this upcoming summer.
Folks have specific questions about the model at this point, and we have one or two people on Google, so I think you can Zoom. You can unmute yourself if you have a question. Okay.
Speak. So I'm curious. Has the use of LLWW and field assessments, has that ever been kind of put together as a means of trying to predict future wetland functions, such as where a stream channel might migrate?
Right. So, you know, we actually did this past year, we made a key where you could go in the field and use something similar to apply the LLWW, and then it basically spits out that code with the crosswalk. And we talked to partners about it, and you know, their thought was that they really wanted to use it more at the landscape scale, as you know, more of this model piece where they're looking at their bigger management areas to see where those functions they need to be looking at certain types of wetlands, or if they've only got, you know, a couple of wetlands that have these specific functions, those kind of things that they could look for rare species and those kind of different things, rather than doing it at the local scale or at the wetland scale. Because like I was saying earlier, you know, really, if you really want to know what a wetland's doing, you have to go and see it. There's only so much you can do at the landscape scale and with this coding, you know, to see, you can see what potential function will be. Like I said, like this wetland should be doing this suite of functions. It should be functioning at this level if condition is there. So you really have to go look at the condition to see if those things are there. Did that answer your question?
Yeah.
Jennifer, quick question about LLWW. I mean, you're working off of the keys for Western United States. Does it work across the country? And if so, is there a urban-rural divide? It's something we think about in the class. I mean, we do a little bit of stuff around Dillon because when you get in urban areas, it's so very different.
Right. That's a good question. So the original key that Tyner built in the 90s to bring NWI together with HGM, that was for the coterminous US. And so that included estuarine systems. And this key does not include the estuarine system. So it kind of shumps off the edge of California and Oregon and Washington. And so it was really built to kind of to focus more on these more arid systems. And I can send you guys the link to that key. It was produced by the Colorado Natural Heritage Program and St. Mary's University. They did that together, and apparently it was a big push to do it. It was not easy. Keys are not easy to make, but we do, like I said, if you wanted to use in your class, we just built a survey 123 that anybody can use, and you can go in and you just basically you start stand there and you say, is it palestrin? It's palestrin. Is it riverine? Those kind of things. You go through it and it basically spits out the LLWW code at the end. Once you go through all those steps.
That'd be great.
Yeah, okay. Yeah, I can easily send those things. And we also, one other thing I forgot to mention, if somebody is interested in this, we built a story map. Can you guys see the story map now on your screen? So it's just the LLWW landscape scale wetland functional assessment. And so this is more about, it has a little bit about the model in it, but the nice thing about the story map, sorry if I'm giving you all a headache cruising through this, it kind of goes through from, you can see the NWI code and how that gets you to the LLWW code in a little, it's just a little easier to see when it's, for me anyway, when it's laid out like that. And then at the bottom, it goes through, you can see the codes from our early models to the existing model and how that's changed. And then the nice thing, it goes through landscape position and it kind of walks you through these different, like here's Lodic, here's the lentic, here's the terrene system, here are the landforms, there's a basin picture, there's a fringe. Oh, sorry, my pictures are not changing. And then these actually change along with it, and there's a floodplain. So the story map is really nice to kind of give you a little background and pictures, which are nice than just talking about codes.
That's great.
Yeah, so I'll send you a link to that as well.
Jennifer, that was a great talk. I missed the very beginning, but thank you.
Thanks, bro.
Yeah, I know. I was just wondering too, and maybe I missed this because I was in late, but the water persistence. How are you kind of getting your persistence on those wetlands? What goes into that part of the model?
Right. So that is a tough one. And so you're talking about like the water regimes from the Corridon codes.
Yeah, and that last last map that you showed of the watershed where you had the late season persistence.
Right. So this is basically based on the LLWW coding, right? So here, these are probably headwater streams and headwater wetlands. So they're assigned a headwater code. And so they're given high potential for helping minimum stream flows, right? So they're part of what helps to keep minimum stream flows where they need to be to support fish populations, right? And so, yeah, so like I said, it is still a coarse landscape scale model. So it's definitely potential function, right? It's not like if you went to that well and you might go, yeah, this is not doing anything for in-stream flows in July, right?
Right.
So, but it's a way for a land manager to go, okay, you know, I know that right in here, this is probably an area, I know that we had, you know, 200 grazing days in that unit. Maybe we need to look at that area as an important area for restoration. We need to do some exposures or something like that. So that's kind of the goal for land managers to use it at a bigger scale. Does that make sense?
No, that's great. I was just trying, I was like, oh, that's really cool. I mean, yeah, because I've been doing some persistent stuff too, but coming at it from a total different way. So I was just wondering how these maps were developed. So that's really cool. Thanks.
Right. The water piece is tough because we have our crews who are not usually wetland scientists go out and collect water regime data. And that is a really hard concept for folks to understand, like, is this seasonally saturated? Is it seasonally flooded? You know, there's water sitting here in July, it looks flooded to me, those kind of things. And so you're right, that is a really tough thing, and it's a very tough one to assign in imagery as well. So when we do the mapping, they kind of have a series of steps that they go through, like we're looking at imagery from different years. And so if you see that it's consistently wet in August, and there's surface water, it's probably got a flooding regime, you know, it's gonna have like an F, semi-permanently flooded, those kind of things. And that's how we get to those. It's not perfect for sure. And you gotta get your boots wet to really know.
Oh, but I was just wondering if you were pulling in outside physical data or landscape components or position but not, it doesn't sound like it.
Yeah, well, I mean, definitely landscape position is included in the model. And so if we have LiDAR, like I said, because those, you know, that LiDAR data is really amazing. It's just a very, very fine scale. Like I said, you can identify species with that LiDAR data. And so getting those really subtle landscape pieces and seeing, you know, that there is groundwater coming out on a gentle slope, those kind of things, those are gonna, you know, revolutionize this kind of modeling for sure.
Oh yeah, that'll be awesome.
Yeah, right.
I'm so excited.
Yeah.
New LiDAR data all for Yellowstone though, which is cool. Anyway,
oh, really? Nice.
The whole park,
Nice.
and it's all public.
Fabulous.
Yeah, so.
That's great. Great to hear.
Thanks, Jennifer.
Yeah, thank you.
Any other questions, or they might be ready to hear about jobs?
Jobs, yeah. I want to loop some people in for sure. So let's see, how did I do? Sorry about that. So just a little bit about, I mentioned this before, probably the biggest projects we do, definitely the biggest projects we do are for the Bureau of Land Management. And we do what's called their assessment, inventory, and monitoring protocol. And that is a very technical protocol that we do in wetland or riparian systems, LODIC, which is aquatic systems, streams, and then terrestrial systems. We do this work, and I put mine first because I do the wetland riparian. And knowing that you guys are learning about wetlands this year, this will be a great opportunity if you're excited about wetlands and you want to see what it's like to collect data in a little more detail in those systems. We're going to do that in Nevada and Idaho this summer. LODIC, so the aquatic systems, we sample in Nevada, in Idaho and Wyoming, and in terrestrial systems, I forgot the Dakotas. We also do the Dakotas and Montana and Idaho and Wyoming. But like I mentioned before we started, I don't know if you've heard this, we are more than willing to base crews out of Dillon, Montana, because we do a lot of sampling in Idaho, and it's actually, you know, not that far to get it down there when we're based out of Missoula. And so these are great opportunities to, like I said, really implement some of this information you've learned. It's long-term monitoring. So some of the sites we implement and we put rebar in, and they go back and look at them year after year to see see changes in the system, and see what their management strategies, how they're impacting the system. Like if they put up an exclosure, are the elk still jumping over and munching the grass to the ground, or was it the cattle that were disturbing the soils, or whatever it is. So these data are used to make informed management decisions on the ground. So it's definitely an applied data collection protocol. So they collect the data for very specific reasons, so they can make these management decisions on the ground. Often they use them the next summer. So we're getting our data in right now. They're going to crunch the numbers and try to use those data for the next field season, which is really cool. And the AIM protocols are being collected at the BLM scale, which is the entire Western US, which is also really, really cool that we've got, management agencies that have decided to start collecting the same data across all of their lands. The AIM protocol was started, I think, a dozen years ago. So they've got some legacy data now at this point to really get a picture of what's going on out there, and in light of climate change and changing hydrology out there, it's a really important piece of the puzzle. So if you wanted to learn more about the BLM AIM strategy and what they're doing, what they do with the data, you can actually get data sets. I know multiple people that have used these data because there's so many for master's projects, which is really, really neat, mostly if you can go out and collect the data and then use it for a master's project in subsequent years. And then also I can send over a link to our site at so you guys can go and find, if you're interested in working for us next summer, you guys can just, send stuff straight to me if you want to, and I can give it to the right person, or you can go and look. We'll start posting our jobs in December. And like I said, you get to see just lots of really cool landscapes. A lot of times it's a random sample. So it'll just be some random tiny little wetland up on the side of a mountain that you have to hike to, and they're gorgeous and, really, really neat places to work and cool stuff to see. You get to see just really neat soils. Have you guys done soils yet? Soils are probably one of the coolest parts of wetlands. And so if you're into soils, that's a neat part of it. We did a soil pit. We look at for hydric indicators. We collect a bunch of information about the hydrology. You look at, your hydric indicators that you're going to see at the site. And then we also do the vegetation piece. That's the hardest part too, for sure, the vegetation. So if any of you are inclined to learn how to ID plants and ID hard plants and wetlands, we would love to have you, because it's really hard to find botanists, that can really get out there and do the field botany, because it's definitely not an easy piece of the puzzle. So we collect all those pieces in the wetlands. In the LODIC system, or the LODIC protocol, they're doing more physical data collection. So they collect a lot of bed and bank data, so they're looking at incision, they're looking at, loss or accrual of vegetation and sediment on the sides of the bank. So there's a big physical piece to that. And the terrestrial sampling is pretty similar to the wetland or riparian. They dig a soil pit, they put out transects and collect vegetation data, and those kind of things. So those are a little bit quicker samples, where the riparian and wetland takes a full day to do a sample at a site. So if you wanted any more information about that, I have flyers that you can look at. We work 8 days on, 6 days off. So it's really nice. You go out there and do a pretty dense chunk of field work, and then you have your 6 days off, which is a really nice schedule for the summer to go out and do your own thing. So that's my plug. It's super fun. Love the field work, and love to get out and meet folks that are fired up about collecting natural resources data. So we'd love to have you if you're interested.
Awesome, thanks. That sounds great. Any questions about that side of it? Or? Yeah, and send us anything for announcements. That'd be lovely. We've got an internal page, and I can send it to our career services. So we have
That's great.
We have advising coming up soon, so a lot of us will be meeting with our advisees.
Okay.
That would be wonderful. Thanks, Jennifer.
Yeah. No, thank you. And yeah, any other questions? Like I said, I could send all this information. Eric's, if somebody is into modeling and into the GIS modeling piece of these kind of puzzles, it's some cool work. It's a little bit of headbanging to kind of figure out how to make these things work. But he loves it and he's really great at it. And I think it's definitely a cool way to bring ecology data together and really, help out the managers at a landscape scale. So yeah, we can answer any of those questions, on the back end if you think of one later. Don't hesitate.
Awesome. That'd be great. Well, how about a round of applause for Woo!
Thanks.
Thanks so much. And I think with that, unless you have any other questions, we'll probably wrap it up for today. And yeah, I look forward to hearing from you some more. And like I said, we can always talk to you about trainings and things down here using the university facilities. So
Great. Well, thank you. You guys enjoy the rest of your course. It looks really fun. I wish I could come and do it with you.
that'd be fun too. All right. Well, see you later. Bye.
All right. Thanks, guys. Bye. Have a good one.